Good morning, guys. Welcome back to algebra. So today we're going to do a review of functions, and it's really important that we try to tie together all of the skills we've been working on because we've really been working on this since about December, and they're all connected, and this is just kind of a reminder of how they're connected. All right, so as you can tell from my giant, beautiful drawing, this is going to be fun. So a function, we defined it as a machine that allows each input to have only one output. And the first thing we looked at was a diagram kind of like this. And we said, if our input is students, each student can have only one age, only one output. So it makes sense to say that Seema could be 14, Garrett could be 14, and Jacob could be 14. So all of you could have the same ages, but it wouldn't make sense if I tried to say Jacob could be 14 and 18. So no input is allowed to have two different outputs. That makes it not a function. And if we look at it in math terms, we can look at it like this with numbers. So if my input is -2, in this function, it gives me an output of 4. If my input is 0, it gives me an output of 0. An input of 2 also gives an output of 4, just like -2 did. But an input of 4 gives an output of 16. So this is also a function. Even though we have two inputs with the same output, there's not one input that has multiple outputs. And here's the math behind that. This function is actually represented by x squared equals y. So my input of -2 replaces this x, and suddenly I have -2 squared, so -2 times itself, and that gives me the output of 4. If I put in 2, so 2 times 2, I also get 4. That's why they both have the same output. But there's no way I could put in, let's say, -2 and get anything out of that other than 4. So I couldn't say, for instance, that -2 has an output of 4 and some other number. It's only ever 4. That's why this is a function. I could also write this function like this. This was our function notation, f of x equals x squared. And notice that the y has changed position. It came first. But the f is just telling you that this is a function of x. So y is determined by x. And I could take that same information and also write it like this. So this is a relation when we write it as a set of ordered pairs. And our inputs are all of the x's. That's why I wrote them all in yellow. And our outputs are all of the y's. And that's why they're in red. So we said one of the ways you could check to see if a relation is a function is to underline each of the inputs and see, do any of them repeat? In this case, we notice none of them repeat. Therefore, each input must have only one output because I don't have any input listed more than once. You should notice that some of the outputs are the same, like we talked about earlier. 4 appears for both -2 and 2. But again, it's okay to have the same output, just like it was okay for you guys to be the same age. I could also take all that information and graph it. So I've already graphed the first point. -2, 4 goes right there. 0, 0 is at my origin. That would be right here. And 2, 4 would be right here. 4, 16 would be way up here. So this is the same function, just put on a graph. And we had a special name for this type of graph. When all of your points are by themselves or when there are breaks in between lines, it's called discrete. And discrete data requires a different way of writing the domain and range. So one of the things that helped me remember that was discrete, think dots. And that's what you can see here. So we said domain is all inputs. And my mnemonic for this one, to help me remember which one was which, was that domain has the word in it. So it's my inputs. And the range is all outputs. So when I go back to this graph, if I want to write my domain and my range, my domain would be all of my x values in order from least to greatest. So -2, 0, 2, and 4. My range, similarly, from least to greatest, I have to start with 0 because that's actually my smallest y value. It's down here. My next y value is 4, but it appears twice. I don't need to write it twice. I can only write it once. And then my next value was 16. And we talked about how you can put an ellipsis, the ... at the end of these to indicate that there are many more possible inputs and outputs. And that is especially true. This is an infinite function. There are no limit to the number of numbers I could put in for my domain or my range. If I didn't, however, have a graph that was all dots or all separated, the word for that type of graph was continuous. And we had a little confusion around this at first. This graph, for instance, is continuous, but notice it has two distinct endpoints. It ends right here and it begins right here. So it doesn't mean that the graph goes on and on and on forever. It continues. It just means that all of the points are connected. So I would remind you, connected means continuous. There aren't any breaks. There aren't separate dots that aren't connected. So my domain on a continuous graph is my least x value to my greatest x value. So it's from left to right. So my x value right here would have to be 0. And there's no way I can list every number between 0 and this endpoint. So rather than using commas and trying to list every x value, I say it's from 0 to, and then I look to see about where it ends. It's definitely not ending at 8 or 10, so I'm going to say it ends at 9, 0 to 9. My range, I'm looking for least to greatest in my y values. So again, I don't necessarily care where it ends or begins. It's from down to up. So the lowest the graph goes in y values would be right here. That would be 2. I'm going to use my TO form to indicate that it's all numbers from 2 all the way up to whatever my highest value is, which looks like it's just below 4. So I'm going to make an wait, is that 4? Sorry, just below 6. So I'm going to make an educated guess and say that's about 5. And if I had any sort of units, so if this, for instance, had said minutes, and this part had said height in feet, I would include that in my domain and range. This would be feet, and this part would be minutes. And our last big topic on this before we got into interpreting graphs was using that function notation. So we said when you see this, you pronounce it as f of x. And it just means that this is a function of x. So y is actually this entire thing at the beginning. It's the f and the x. That whole thing is y. So my function is 2x plus 3. And the first question I'm answering is, what is f of x if x equals 4? So I've been given a value for x. So that means this is my input. And I'm going to put it into my function to get my output. That's what f of x will be. That will be an output. So I start by writing the function exactly the way I see it. And then I look. Everywhere I see an x, I'm going to put 4. So f of 4 equals 2, and I put my 4 in parentheses, plus 3. So there's nothing I can do with f of 4. That stays the exact same. But I can simplify the right side of the equation. 2 times 4 gives me 8, plus 3 gives me 11. So that means that 11 is my output when I put in my input of 4. And this is important because it gets a little confusing when we switch it around. So on question 2, it asks, what is x if f of x equals 9. So I haven't been given an input. Instead, I've been given an output. I need to find my input. I need to find the value of x that gives an output of 9. So I'm still going to write my function. But this time when I go to rewrite it, I'm looking at f of x equal 9. So this whole thing will become 9. And I'll write the rest of the function. So this is an equation that we know how to solve. So I can draw my line. I'll perform inverse operations to isolate my variable. My last step is to divide. And I find out that when I put in 3, I get an output of 9. So what I've solved for was my input. And if I wanted to write it as I did number 1, it would be f of 3 equals 9. All right, so give the quizzes a try, see what you can make of it. Remember, I am grading for accuracy, so take your time. Use another sheet of paper. I should have given you plenty of time on the timer. Actually try these for me, okay? And I will see you later.